In physics, there is a concept called ladder, and today I'm going to talk about ladder, because if you know ladder and how to build a ladder, and you know its tricks and its advantages, you can develop very advanced theories in physics. So what is ladder? So you will often find that in a particular scale, a particular property is generated. However, if there is a conservation of some symmetry across scales, so if you say in the nanometer scale, you see something, say 5 to 10 nanometer, and you are doing some study and you find that there is some particular properties. But one of the key feature that is controlling it is phase, and phase is quantized, say 45 degree, 90 degree, 135 degree, 180 degree, something like that, for different states. And you go to the higher scale, and again phase is conserved, and again you go to the higher scale, micrometer scale, millimeter scale, centimeter scale, and you find that there is a conservation. So whenever there is a conservation and you go there, then you find that this kind of situations happen. Then we call it a ladder. For an example, if geometric phase is conserved. What is geometric phase? Geometric phase is a phase that depends on the path, as a function of path, and not as a function of time. So if geometric phase is responsible for a particular system for its evolution, then if geometric phase is conserved, a set of geometric phases at different scales remain conserved, then you can say it's called Berry phase ladder or Pancharatnam phase ladder. In case you find that frequencies and ratio of frequencies remains constant at different levels, then you call it conservation. You don't say conservation, but you call it a ladder, just like frequency ratio ladder, and or you can say symmetry ladder. That means each resonance frequency is associated with a particular kind of symmetry breaking. So if the ratio of resonance frequencies are constant across different scales, then you will find that there is a control on the symmetry breaking across multiple scales. Then you say symmetry breaking ladder, or you understand the fundamental rules how different kind of symmetry breaking events could be correlated. Now there are many applications of this kind of ladder. For an example, a fractal growth. So we were synthesizing a nanowire from single molecules, and the molecule it created a helical nanowire, then helical nanowire created gel, and then it went on from millimeter scale to centimeter scale, nanometer, micrometer, centimeter, millimeter, and then all these different kind of scales. And then we found that that this went on increasing at various different scales. Normally what we expect, we would expect that it would give similar property like atomic scale or molecular scale. Have you understood the significance of it? It means that you encode some properties or features in the molecular scale, and that is again transcended to the classical scale. So there is a bridge between classical and quantum, and if you want to understand that, then this ladder or the concept of this ladder becomes very important. So you have to always remember this ladder. Imagine in the 1920s, S.N. Bose was calculating the statistical distribution of entropy and KT in different compartment and different scales. So he took the values of probability distribution, took the logarithm at both sides, and got the Bose-Einstein condensation, the Bose-B statistics. Then you get ME statistics. So this kind of different statistics they got. So you may think that this is a very simple feature, but this was a case of a ladder where the compartments, the properties of different compartments at various different scales remained constant, and that's why distribution of function at the different scales followed a singular principle. Isn't it beautiful that you create a statistical law based on this ladder? Now suppose there are some nonlinear optical properties. Even then you will find the concept of ladder is being used. Even when you talk about, say, photoluminescence of a very large scale, a quantum property that is generated at the molecular scale is scaled up to a very large scale. Even some properties like piezoelectricity, then magnetic properties, when a large number of energy levels that are coupled all across the material, and there is a distribution at various different scales. So then you can apply these conservation principles across the scales, and then you can implement the ladder concept. So I have seen use of this ladder concept many cases. What do? They create an infinite series. Suppose initially this is the term, then second order term, third order term, fourth order term, fifth order. Yes, you heard me right. So whenever you use this kind of principle of many various different orders of interactions on something, you are basically trying to build a ladder. So that's why by creating these ladders and differentials of various orders and degrees, what you try to do is that you try to find out at various different scales what are the properties that would remain. But in most of the cases, what happens is when many physicists, they get deviated by, because I have to use dy dx, d2y dx, d3y dx2, d4y dx4. So when you go by this way, you assign that my higher orders are only the differentiation of the lower orders, and as if some sensors are sitting over there to do this. So this trick is widely used for the last 200 years, but this is not a very good one. In other way, statistical distribution is also not a good one, because it also has a limitation when you create the ladders. Because you consider at every different scale the compartments have similar properties. That is the problem with B statistics or FD statistics or whatever the statistics is. But imagine you have different scales and different kind of rules of compositions, and that's why our phase prime metric comes in. And that's why we want to create a new statistics, new way of looking into the ladder systems, not differentials, not just identical compartments, but at different scales, different composition of prime number of components come together and generate properties from the composition and ordering itself. Isn't that beautiful? So that is the new kind of ladder that we want to introduce in physics.